Give people a few more minutes. Okay. Here we go. What in the heck? Here we go. Okay, so we're just about ready to get started. Do we have any questions before we begin? Everybody's good? All right. So today we're going to talk about sampling distributions. And specifically, we're going to talk about sampling distributions for sample percentages. And it turns out this is going to be one of the really, you could say, foundational parts of this course, something that you really do want to understand well. And so I'm going to review what was in the summary videos very briefly, just so we're all on the same page as far as what we're looking at. So in that summary video, it talked about a poll taken by CNN, and it was taken regarding whether or not people would vote for Trump, and there were 766 people in that poll. And what we want to know is if we keep on taking random samples from some population where we assume we know the population percentage. So let's just suppose that 50% of the population would say vote for Trump. And we kept on taking random samples of 766 people and computing the sample percentage from that, and then putting it back in and doing this over and over and over again. So we had all of these random samples that had the same size. And what we were really interested was the sample percentage from each of those samples. And we could go ahead and plot those. Notice that our data is categorical. It only has two possible values, yes or no. But what we compute from our sample is quantitative. It's a percentage. And we're really interested in what this pattern that the estimators make looks like, okay? And one of the things that we saw in this part of the course is that these sample estimators, they don't have a random pattern. In fact, they have a pattern that we've already visited, we're very familiar with. They have a normal distribution. However, before we can come to that conclusion, we need to make sure that our sample is good. And good here means that it's random and large enough. So as a very brief reminder, okay, pi is not the number pi, okay, in this context. It's a number, but it's the percentage in the population in our category of interest. So in the election scenario, it's the percentage of whatever population of registered voters who are in my category of interest, which is they'll vote for Trump. We take the sample percentage is small p. So when we're talking about percentages or proportions, you always have to ask which one. Am I talking about the population percentage, which is a parameter, or am I talking about the sample percentage, which is a statistic, okay? Meanwhile, we have the estimator, okay, which is different than the variable. It's a summary statistic of all the values in my sample. And again, we have some notation and we have to be careful with this, okay? If I were to take samples over and over and over and over and over again, I would get the population curve, right? Remember that the plotted histograms, we're always trying to figure out what the population curve is. And of course, this has a normal distribution. So there's a mean, okay? Population mean of all the sample percentages. So again, you want to remember that that thing that looks like a U is actually the Greek letter for M. It's mu, mu sub P. This is the population average of all the sample percentages, P. And there's also a sample standard deviation, and that's sigma, sigma sum P. Population standard deviation of the sample percentages. And meanwhile, in that example that we ran, that simulation, we had a sample mean, not a population mean, but a sample mean of our sample percentages. And sample mean is not mu, that's population mean. This is X bar. And the sample standard deviation, which instead of the Greek letter for S, sigma, we just used the regular Greco-Roman letter, S. So these are pieces of notation that you either want to write down or have somewhere handy or understand what they mean, okay? Questions before we go on?
So when typing these into like Excel per se, so like, because Excel is a lot more complex than StatCrunch, you would, for trying to find the population mean of a sample, you would just type in the mu sub P.
Okay, so we're getting a little ahead. We're going to get there. Just kind of hang with me, okay? And actually, in the video, I show you how to get X bar P and S of P. I actually show you in the video, so you can go back and watch that. But mu P and sigma P, we're going to show how to get, and we don't have to use Excel. This comes from the central limit theorem. Okay, so the central limit theorem says if our sample is good, random, large enough, we always have to check these conditions, okay? So this is the percentage in the population times the sample size. It has to be at least 10. And the same is true for 1 minus the population percentage times N. This also has to be at least 10. Always have to check those conditions. Then mathematical theory tells us that the sample percentages drawn from a population with percentage pi, I don't want P there, change that really quick, okay, has a normal distribution. So this is what the central limit theorem tells us. It tells us that if we satisfy these conditions, the sample percentages come from a normal distribution. And they're centered around the population value, which is what we expect, and they have this standard deviation. So you might want to go back, if this notation seems unfamiliar, you might want to go back and review what we learned when we talked about the normal distribution. And one thing I'll just mention really quickly is that, you know, this class is maybe a little different than your other classes. I know in some classes, you can learn a material in chapter 1, and then the material in chapter 2 has nothing to do with chapter 1. This certainly is not the case with statistics. So this course is very much cumulative in nature. So, you know, the things that we learned way back in chapter 1, we're going to find, or in module 1, whatever, we're going to find where we are using. Statistics is a process, and all the steps in those processes are interrelated. So that's kind of important to bear in mind as you're learning this. Okay, so sample size, so larger sample sizes are better, and the question is why? So here's kind of an interesting fact. Everyone knows that larger samples are better, everything else being equal. You've known that since grade school, but none of you know why. And this is what the central limit theorem tells us. Okay. So using this kind of conceptual picture, right, that we talked about before, this is the target analogy where the bullseye, the thing that we want to hit, is population parameter value. The shots, what we actually get from the samples, are the samples estimates. And when you have smaller samples, the estimates are more spread out because you can't average the extreme values as much or as well. Whereas when you get larger samples, you get better averaging, and they're closer to the bullseye or the population parameter. And so this conceptual picture is kind of airy-fairy, it makes sense, but we want to get a more quantitative understanding. And so if we kind of start using what we know, okay, we know that the spread of a data set is given by the standard deviation. So large samples have lower spread. That means the standard deviation has to be smaller. Conversely, smaller samples have more spread, so the standard deviation is going to be larger. But how do we compute the standard deviation from the sample size? And this is what the central limit theorem tells us. It tells us that the standard deviation is given by this formula. Take the population percentage times 1 minus it, divide it by the sample size, and take the square root. And so this shows us what happens as the sample size gets larger, as n gets larger, this fraction becomes smaller, the square root becomes smaller, the standard deviation becomes smaller. So now you understand why larger samples are better. And so this is a really quick example just to kind of illustrate this, okay? This is the sample percentages, population of sample percentages taken with two different sample sizes. So you can see that when n is 25, okay, the population of sample estimates is more spread out, just like here. When the sample size is larger, when n is 100, we get this blue curve. We see that they're closer to the population parameter, and that's what you're seeing here. So this is kind of the idea of what's going on. Are there any questions we have with this picture? This is a really important picture, actually.
I do.
Yeah.
So trying to put it in like another kind of analogy kind of way, it's like, so like say like the bigger the funnel, I guess, the smaller the spread's going to be. So it's like a funnel kind of a thing. Whereas if it's like that, it's just going to like get bigger at the bottom, kind of like a reverse thing. I don't know. I'm probably making no sense at all, but it's like the bigger it is, the smaller the focal point is going to be.
So the bigger the sample size, the less the spread, and kind of the intuitive way people explain this, but it isn't correct technically. People kind of explain this by saying that that the extreme values are averaged better, and that is true. But the problem with that explanation is it doesn't give you a quantitative formula. In other words, what I want to know is, given a specific sample size, what is the standard deviation? I want to be able to compute it, okay? I don't want this conceptual picture. And so this formula, this comes from the central limit theorem, mathematical theory. It says as a sample size gets larger, the standard deviation is going to get smaller. That's what we're saying there. Okay, so what I'm going to do now is I'm going to go ahead. Go ahead.
Can I ask a question about the previous one?
Yeah.
With the formulas? Pi is the sample percentage, right?
Population percentage.
Population
yes.
percentage. And you calculate that from your study that you do, and then you plug it in, or how does that work?
So you have to know that. Okay, you either have to guess that. In fact, when we go to hypothesis tests, which you're going to start on actually with the error barometer discussion, you're going to make an educated guess as to what pi is. But sometimes we're going to see also we get that from historical data. And when we get the hypothesis test, we'll talk about it more. For our purposes, for the problems that we're going to do in chapter 5, it's always going to be given.
But just if in practice, when they actually use it, if they don't actually know what the population percentage is, then like what is the value of the data they're calculating from this?
So what I'm going to tell you is stay tuned till we get the hypothesis testing. You're a little bit ahead of the game.
Okay.
But here's the thing, it's an excellent question, and I'll tell you why. Because we've been saying all along that we never know the value for pi. It's the population parameter, which we can't get because we can't get everyone in the population. And yet I'm telling you to substitute in pi. How can I be doing that? But I guarantee you, it makes sense, and you'll see how it works. Okay.
Okay.
Excellent question, though. Okay, so I'm gonna go back over now to the problems. I want to get some problems in so we can so you guys will be ready for the homeworks and everything.
And it's just the representative symbol. We're not actually taking pi, right?
I'm not quite sure I follow.
Like kind of like how n is just a symbol for whatever value you plug in. Pi is just a symbol. Exactly
right. It just stands for whatever the value. So in our election example, pi was 50%. percent, but it can be whatever the population percentage is, exactly. It's just the symbol that stands for it, yeah. Okay, so I'm gonna go over to My Math Lab. You can't go through Canvas, but if you open up My Math Lab, you'll see an assignment, and you might have to go down a list a little bit, called Homework 5 Practice. And I'm going to work through those problems today. Okay. I can't emphasize how important it is that you work along with me. Please don't just watch me. Don't be an observer. It's very easy to follow somebody, to watch what they do and understand what they do, but to be able to do it is something different. Like you know, when I'm watching boxing with some guys, right? Invariably somebody will say, "Oh, I wouldn't have missed that jab." And it's like, you have to be joking. You would never get to that point, right? You would be out in the first 5 seconds. It's easy to watch somebody do something and understand what they're doing, but to be able to actually do it yourself, to get in the ring, is a totally different thing, right? And it's especially important in these problems because you have to use your computer. And guess what happens when you go home at 1 o'clock at night, when there's no one there to help you and you try to do it on your computer? Something goes wrong and there's nobody to help you. So if you work on it right now while I'm working on the problems and you run into difficulty, you can ask me and we can clear it up right now, okay? Okay, I'm gonna skip the first couple of problems because they're easy, and actually I've already covered it in the intro.
Do you want us to have a StatCrunch open for this, or do you want us to have Excel open for this part?
Actually, you're gonna need both, Excel and StatCrunch. And you don't have to have Excel open, but I'm gonna show you a nice little hack that you can use. You don't have to use it. You can use your calculator for this. Doesn't really matter, but it will help a little bit. Okay, so this first problem says, consider a sampling distribution with, and they really should have pi. They have p, they mean pi here, and sample size of n each, and we're looking at samples of different sizes. Use the appropriate formulas, find the mean and standard deviation of the sampling distribution of the sample proportion. Okay, so what's going on? So what's happening here is we're looking at the sampling distribution, and what that really means is a sampling distribution is a distribution of sample estimates, and in our case we're interested in the sample percentage. And so the central limit theorem tells us if our sample is good, and we're kind of assuming it is here, okay? These sample percentages are going to have a normal distribution, so kind of like a bell-shaped curve, if you will. Okay. They're going to be centered at pi. This is going to be the mean. Okay. And the standard deviation is going to be given by this formula. Pi times 1 minus pi divided by n, square root of the whole thing. Okay? And so notice that there's nothing mystical about the sampling distribution. It's just another normal distribution, right? It's a normal distribution where the mean and the standard deviation, happen to be given by values that are related to the parameter and the sample size, okay? But there's nothing mystical about it, okay? This is the mean, this is the standard deviation. Now we're gonna anticipate the fact that we're gonna do this calculation multiple times, okay? So what we're gonna do is we're gonna open up an Excel spreadsheet. So open up a fresh Excel spreadsheet. And this is actually in the back of the PowerPoint. And I'm going to put everything I need to compute these values, okay? So I'm going to blow up the size here so you can see it a little easier. And so I'm going to need the value of pi, right? I'm going to need the sample size. what I want to get is I want to get, because here's the thing, I want to do calculations with this normal distribution, right? And what did we learn in module 4? We learned that to do calculations on StatCrunch with a normal distribution, you need to tell StatCrunch the mean and the standard deviation, right? And so that's what we need to figure out. Okay, and I'm just gonna paste this over here and change this from mean to standard deviation. And I already know what these things are. The central limit theorem tells me. It tells me that the mean of the sampling distribution is the population parameter, pi. And it tells me that the standard deviation is going to be equal to the square root of pi times 1 minus pi divided by n. And I take the root of the whole thing. Okay. So everybody's good on this part so far. And I'm just going to make my table look kind of nice.
1 second so you can like copy and paste what you wrote down.
And I'm going to put the input here. I'm going to put the input in different colors. Okay, so this is going to be the values I need to input. So in my example, and this is where you got to be careful and follow along, I'm going to put in whatever my percentage is. So mine is 0.11. Yours is going to be different. Okay. I'm going to go ahead and put in 0.11 as a decimal. And my sample size here is going to be 4,000. So I'm going to enter 4,000. So just put in whatever those values are in your problem. And the beauty of Excel, it's not good for statistics, but it's really good for doing repetitive calculations, okay? And I'll show you why. So now I want the mean. So all I'm going to do is I'm going to type equals, and I'm going to click on the cell where the value of pi is, because, well, that is the mean, right?
Can you show the rest of the equation that was for column D?
I haven't done it yet, and I'm going to do it. So hang on, you'll actually see it again, okay? So don't worry. We'll do one thing at a time. So first of all I'm going to do is I'm going to put equals A2. Notice I'm not typing in the value. This is telling Excel put in cell C2 whatever's in A2. So that means if I go to another problem and I change what's in A2, C2 will automatically change. And I don't know about you, but you know, I'm lazy. I like that. Now I'm going to compute the standard deviation, okay, of the sampling distribution for the sample percentage. Whenever you want Excel to return a value, you always have to type equals first, okay, for any formula. And when you start typing in the command for square root, it automatically brings it up. You double click on it. And again, I don't want to enter the number, right? Because I'm going to change pi. So I'm going to tell Excel, okay, whatever's in this cell, use this, and then multiply it by 1 minus whatever in that cell. And then divide by the sample size. And you can see that Excel is super cool in that it actually color codes this. If you look carefully, right, the sample size where the cell is, it's actually in red. And that's just super neat. I just love that part. And then we type and we hit enter. Okay. And that's it for pit.
So it's not exactly doing that for mine either.
So let's see what you're doing. So this is a really good thing. This is why we do this stuff. Well, I'm going to go ahead. I'm going to let you share. You're going to become a co-host. Let's see, Kristen, you're a co-host. Okay, everybody, give her a big hand. Okay, so now you can go ahead and share your screen and let's see what you're doing, because you're not the only one that has trouble with this, trust me. And that's why I go through this.
There we go.
Mm-hmm.
So For this one, I put in the,
Nope, nope, no, stop. Type it in one time. Don't do that because you'll get the wrong answer. So go down to D2 and type in equal. Now square root SQR. There you go. Okay. Then you click on where pi is in A2. Okay.
right here.
No. On A2, you're going to click on A2. So, yeah, see? And now you put a times. So that's pi times. So you put a little star sign. Now you put a parenthesis. 1 minus pi, which is in A2, right? So you go back and click on A2. Close out your parentheses. Division sign. There you go. You got it. And actually, you can be lazy and just hit enter, and Excel will automatically auto close. So go ahead and say yes. So it's giving you a snarky little command. It's saying you didn't close off the parenthesis, and sometimes it will do it by default. Piece of cake, huh?
Yeah, thank you very much.
Absolutely. Okay, so let me go back to share screens now. Okay. So, and this is the reason why I don't like Excel, because notice that you have to pay special attention to the syntax. And later on, we're going to get to hellaciously complicated formulas. Trust me, you don't want to do it. So is everyone else good? Any other questions we have? Now, that's going to save you a lot of trouble. Here's something else super cool. Yeah, go ahead.
Can you just take a look at mine really fast to see if I did it right?
Well, I tell you what, let's do this. Let's go ahead and put in the answer. If you don't get the right answer, then we'll come back and revisit it. Okay.
Sounds good.
Now here's what's super cool about Excel too that I like is you can click on a cell and you can regulate the number of decimal places. So if you look at the top menu bar, you'll see something called menu in the center. And I want 4 decimal places. And you know, I hate to round, I'm lazy. So I click that and it rounds it out to 4 decimal places. And I don't know about you, but I'd much rather do that, okay? So go ahead and enter your values. The moment of truth has arrived. Okay, we got that right. And of course, yours are gonna be different, right? So mine is 0.0049. And we done did it. Okay. Before I move on, I wanna make sure that everyone gets this right.
I did not.
Okay, so let's see. So I'm gonna make you, so can you tell me your name really quick? Because I got so many people on the list.
Jack.
Yeah, okay, Jack, gotcha.
Yeah, I'm in the same boat too.
Okay, let's see. Okay, Jack's our co-host. Hands for Jack. Okay, show us what you got here. And you're gonna have to show us your problem too, because you're gonna have different numbers, right?
Okay. How do I share the screen?
Yeah, please. Exactly.
No, I said, how do I do? Oh, never mind.
Oh, yeah, at the bottom. Sorry. Yeah. Sorry, at the bottom of the thing. And by the way, if we don't get through all the problems, I will actually work through all of them myself and post before I post the video, okay?
It's, you have it disabled for me to be screen sharing.
I have you as co-host, or do I? Let me make sure. You're a co-host. Okay, maybe I didn't. Okay. Well, hold on. Make sure I got the right person. People are moving around my list.
Okay, I think that.
Yeah, you're all good. Yeah.
Okay. That's better. So this is the question. And then.
Now, are you using the numbers that they were given in the problem?
Yeah, 0.8 and then 5,000.
Can you show me? You know what? I think you didn't. Can you show me your problem? I actually know what happened. Show me your problem.
Okay.
It isn't 0.8. I'm pretty sure. And by the way, that isn't the mean, right? You entered the formula for the standard deviation, so you have it in the wrong column. You actually want that in D, right? Yeah, you can copy and paste it right into D, or cut and paste it.
Well, actually.
Yeah, Excel can be kind of quirky like that. Can I give you a little hack? Go up to the command bar. See that bar above?
Up
And
here?
copy and paste from the command bar. Yeah, there you go. Highlight that. Control X, Control C, enter. Okay, now there you go. Don't worry about the false stuff. Just let it. Yeah, you can just delete it. Okay, that's equal to A2, right? And C2 you want to hit equal A2
C2
because
is equal to
right
A2.
because the mean of the sample percentages is the population percentage. Okay. So was that the problem? Were you entering?
I think I entered the wrong thing.
Ah, okay. Try that and see, okay? And we will wait. We'll see. So other people that were having trouble, was that the same thing or was it something different? Somebody else said they were having problems.
Yeah, that's right.
Excellente. Everyone else good. This is an important calculation. We want to get this down solid. Hello? Okay, I'm going to assume then. Yes. Okay. Back to our regularly scheduled program. Okay. So, and I'm not going to do the other ones because you guys can do those now. Do we have a question? Can you speak up? For some reason, I can't really make out what you're saying. No other questions? Okay, so for these other problems, the mean's always going to be 11%. Notice that the sample size, the only thing that's changing here is the sample size. And if you go back and you look at this PowerPoint, right, the sample size does not affect where the normal distribution is centered, and that's the mean, right? It only controls the standard deviation. So for all those other points, all those other problems, the mean is going to be the value of pi that you have. And all you're going to do, and let me just show you really quick how this works, because this is one of these things that actually, it's really nice to see how Excel works. I'm going to do problem 2 very quickly, and you can do it too if you want. So notice that in this problem, my pi is the same. The only thing that changed is my sample size. So all I do is I just change, oh, crap. Hold on a second. Let me get out of there. All I do is I just change the sample size. That's it. And now watch D2. Okay, watch what happens inside cell D2. Right now it's 0.0049, right? It automatically changes. Isn't that cool? Okay, so you can do all of those calculations now. All you have to do is just change the sample size. Okay, shall we go forward? Let's try. Okay, so yes, question? Is there a question, or so let me just make it. Let me make a request, please. If you have sound going on, yes. Okay, is there a question, or is this background noise? We have to move quickly, guys.
I think they're upstairs. I think you waited for everybody else to rotate.
Okay, I'm gonna go on. And please, can you mute your microphone when you're not talking? I really appreciate it. Okay, that way we don't have to have all these interruptions. Okay, for a population of people who suffer occasionally from migraine headaches, suppose P, and they mean pi here, is 80%, and that's the proportion of people who get some relief from taking a certain medication. For a particular subject, let X equal 1 if they get relief, X equal to 0 if they do not. And we want to consider a random sample of 46 people. Okay. So what they're asking for here in part A is they want to know the probability distribution for each observation. And what that means is they want to know what is the probability that a randomly chosen person, one person, is in your category of interest, which here is that they get some relief. Okay? So that's what this is asking. So let me just copy and paste this into OneNote, just so this is really clear. So when they say something like probability for each distribution, probability distribution for each observation, what they mean is the probability a randomly chosen individual falls or is in our category of interest. Okay? And for us, in our problem, category of interest is that they get relief. Okay, so that's what that problem is asking. Okay. So we're given that information. We're told that there's an 80% chance a randomly chosen person will get some relief from taking the medication. Now, in some of these problems, there's some distractors, okay? So notice that in my B and C, and these might be different choices for you, they're talking about the number of people from the sample. That's not relevant. We're interested in the individual. So it can only be A and D. So A, it says for each observation, the probability that medicine helps is 20%. The probability it doesn't is 80%. But that isn't what the problem is saying, right? 80% is the proportion who get some relief. So the answer is D. For each observation, the probability the medicine helps, which is what it means to get some relief, is 80%. Does that make sense? Is that reasonable, do you think?
So because it wasn't like quote unquote a random sample, it was an observation that was made.
Right. When we're talking about observation, we're talking about one randomly chosen person.
Okay, and if it were a random sample, it would be more than just one.
There'd have to be language. So you'd have to see something like, state the probability distribution for the sample percentages, something like that.
Okay.
Okay, we'll check to make sure. We got it. Okay, so now there's going to be some more parts to this. Find the mean of the sampling distribution of the sample proportion to get relief. This is just a fancy way of saying, what is the mean of the sample percentages? And we know that's always the population percentage. Okay, that's always the case. The central limit theorem tells us that. Now, one thing I'll mention really quickly, the book is sloppy. The book doesn't check to see that the central limit conditions are satisfied, okay? They should, but they don't. So be a little careful. Generally, they let it slide. Okay, so we check our answer. We've done good. And so now they want the standard deviation. They want to know, okay, if we keep on taking samples of size 46 from this population, where the population percentage is 80%, we're going to get that normal distribution for the sample percentages. What is the standard deviation of that normal distribution? And guess what? We done did it, right? That's that Excel calculation. So go back to Excel, bring up our sheet. And notice the cool thing is all I have to do is change the sample size and the population percentage, right? So for my case, it's 0.8. And my sample size is 46 in my problem. And of course, we answered B already, and this is my standard deviation. And I conveniently already rounded that off to 4 decimal places, so I just type it in. Okay. Does that look good? Is that kind of coming together?
Yes, sir. So we use that same equation for a lot of this sampling distribution means and standard deviation.
Right, exactly. This is telling us, so this is telling us the pattern of estimators, So we know that the pattern of estimators is normal, and now we just want to figure out, okay, what sort of normal distribution? And to uniquely identify a normal distribution, you need to tell me the mean and the standard deviation. And we know the mean is pi, and this comes from mathematical theory, okay? People actually knew this a long time ago. This was known from empirical observation. What they didn't know was the standard deviation part. And there's actually a very famous incident that happened in Britain. It's called the Tale of the Picts, where people who did know this, they were kind of like the quants of their day. They actually skimmed gold off the British treasury because other people thought this formula was different. They thought the n didn't go under the square root sign. And so the people who knew this skimmed some gold and they made off with some. I don't think there's anyone alive that had the amount of money that they had at the end. I mean, alive in terms of today's dollars. They made that much money off of the gold they skimmed. So, kind of like Office Space with the pennies in the jar, you know? So cool. So cool stuff.
So
Okay.
for our discussion
Yeah.
board, can we use this same equation to help with our discussion conversation?
No, this won't be relevant in 5, but it is going to come up later on when we start to talk about hypothesis tests. No, I take that back. Actually, you are. I take that back. Not this week, but next week, because we're going to continue the discussion board into next week. You're going to use this formula.
Mm-hmm.
Yeah. Okay. So explain what the standard deviation. So this is actually what Kristen just asked. This is the standard deviation of the sampling distribution. It's the standard deviation for the distribution of sample estimates we get. Okay. And there he is. Okay. The next question is kind of asking the same sort of thing. Okay. Again, binary categorical variable, right? 1 means you're in the category of interest, okay? 0 means you're not. Sometimes people call this an indicator variable. It's indicating whether the person is in your category of interest, right? And so in an exit poll for which the sample size was 3,150, suppose that 75% of all voters voted for a recall. Now, one word of warning. Whenever you see a percentage, especially in this context, you have to ask, what is it? Is it a sample percentage or a population percentage? And you might remember we had some homework problems that tested parameter versus statistic, right? So parameter is when it comes from the whole population. Now this is a little tricky because on the one hand, you see all voters, okay? The question is, what all voters were they? Were they all the voters in the sample or were they all the voters in the population? Okay. When you read into this problem a little more, you'll find out that this is pi. This is all the voters in the population. Okay. But you always have to think about that. Notice you have two percentages running around, right? You have the population percentage, which is a fixed number. And then you have the sample percentage, which is a variable. It changes from sample to sample. They're different things. You need to be careful, okay? But this is asking the same sort of thing. So we know that pi is 75%. So there's a 75% chance an individual that's randomly chosen will vote for the recall. And that's what they're asking for here, right? So they want to know that describes the probability distribution for the individual. So let's see, we can roll out this one, B and D, because again, it's dealing with the sample. And here they mix these up, right? So the probability of success that the person's going to be in our category of interest is 75%, okay? And click yes. Okay. And now they're going to ask us similar questions, right? What is the mean and what is the standard deviation? So how am I going to answer this? How am I going to compute those things? I'm going to use the formulas from the central limit theorem, right? So this is my pi. Again, your number will be different, but mine's 75%. So I'm going to enter that for pi. And notice now that I know that has to be pi, right? I need the value of pi to get the mean and the standard deviation of the sample percentages, right? So there's no other percentage given. So this has to be the population percentage. And I'm going to enter the sample size, and you can enter yours. And now I know everything I need to know. And let's round it off to the right now, the decimal places. Okay, so, and the thing is, watch with the rounding. Don't always assume it's the same number. StatCrunch can be, I mean, my math lab can be kind of devious like that, right? Okay. So this question here is on a different track, okay? This is using what we learned way back in module 4. We talked about the normal distribution. So let me bring that up really quickly. We go back to module 4. And I think it was part 1. We'll find out. You might remember we talked about something called the empirical, actually it's part 2, I just remembered. We talked about something called the empirical rule, right? And the empirical rule told us how likely we are to be to be a certain distance from the mean in units of standard deviation if we had a normal distribution. Way over here, we had this thing called the empirical rule. So the empirical rule says that there is a 99.7% chance that a randomly chosen data value from a normal distribution, a population that has a normal distribution, is 3 standard deviations from the mean. So this means it's very unlikely to get somebody that's more than 3 standard deviations from the mean away. And that's what this problem is dealing with. So remember how I said everything's interrelated, right? So now we're going back to module 4, where we're picking up this piece of information. And that's what they want you to use. So in an exit poll, suppose the mean of the sampling distribution of the proportion of 314 people in the sample who voted for recall was 0.65. And here's the thing, when you read these problems, okay, sometimes you're going to have to read them more than once, more than twice. Okay, that's a long sentence, okay? So this is the mean of the sampling distribution of the proportion. And so I'm looking at the mean of the population of sample percentages. And in this case, it's of the 3,140 people, okay? So my pi is 0.65 because the mean of the sampling distribution for the proportion is pi. That's what the central limit theorem tells us. And they're actually giving you the standard deviation, okay? So what they're asking you is they're asking you for the interval that contains 3 standard deviations of the value. So they're actually asking you for this interval right here, from the point that's 3 standard deviations below to 3 standard deviations above. That's easy to do, right? In fact, if we wanted, we could do that in Excel. And so let's go ahead and pull this up. So our mean here, you can just type in whatever this is, minus 0.65. The standard deviation they give us, we don't have to even compute it, right? It's 0.0085. And so 3 standard deviations below is just going to be equal to the mean, and I'm just going to subtract off 3 standard deviations. So minus 3 times whatever's in the cell for the standard deviation, right? And if I want 3 standard deviations above, all I'm going to do is alter the formula, and instead of minus, I'm going to put plus. Hold on a second. Oh, never mind. I'm confusing myself. So I'm going to cut it here and paste it, hit enter, and then click here, and in the formula bar, place my formula and make this plus. And there he is. Okay. Everybody getting that to work out? So we haven't talked about Excel, okay? I'm showing you how to do basic arithmetic operations in Excel using cell contents, okay? And if I look really carefully, I have to round it off, looks like the 3 decimal places. So that's 0.625, and that's 0.676. That's gonna be my answer. Check it, I'm good. So this is what they mean when they say given interval which contains almost all of them. Okay, so this is the phrase will almost certainly fall. Okay, that's what they mean. All right. Questions?
Yeah. So that equation that you used, it was the C5 minus whatever.
Yeah, so what you're doing is you're just clicking on saying equals, and you're clicking on the mean, and then you're subtracting 3 times, and you click on the cell wherever the standard deviation is. See? So this is a cell where my mean is in C5, minus 3 times, and you click on the cell that contains the value of the standard deviation. And of course, you know, I cold-bloodedly did that because there's going to be other problems where we have to do this also, so it's going to be helpful. Okay?
Mm-hmm.
Working? Yes? No? Not sure?
Yes, I forgot I was muted, sorry.
Okay. So go ahead and try that. Make sure you get the right answer. And if you don't, let me know. We need to stop and look at this, because again, and again, you can do this, all of this in your calculator, okay? There's nothing, you don't have to use Excel. It's just that Excel makes it easy because when you want to do the calculation over again, rather than retype it in your calculator, some of these formulas like standard deviation can get to be a little tricky, right? Just change 2 numbers, it updates everything. All right.
So the when it comes to the I guess saying if the result is usual or unusual, you would have to say yes, it is because it's outside of the proportion lines or inside.
So yeah, so let's go back and look at what the empirical rule is saying. It's saying that we would expect, it would be usual for this value to fall in here because 99.7% of the values are in here, right? It would be unusual to have an extreme value. And you can see it's unusual because there's very little probability in this tail, right? So if something falls outside that 3 standard deviation window, that would be considered unusual.
Okay.
And so what we're going to do is we're going to look at our value we're given in the next part of the problem, and we're going to ask, does 0.66 fall in this range? And in my case, it does. So it wouldn't be unusual. So I know that it's no, and it's no because it lies in the interval. Now your value may be outside. I mean, don't assume it's inside, okay? That's how they fool you, right? And you have to watch the wording. Okay? And that's kind of how, even though I tell you guys not to use the box plot as a test for outliers. That's kind of how the outlier system works for flagging outliers. It's kind of like that. When it's so far out in the distribution, it gets flagged as an outlier. All right. Okay, so this is a baseball player in the major leagues who plays regularly, will have about 600 at bats, okay? There's about 600 times that he gets to be a hitter during a regular season. Suppose a player has a batting average of .347, okay? So this is his actual, this is his real batting average, so God knows that he's really a 347 hitter, okay? That's what the true percentage is, pi. So it says his batting average at the end of the season is the number of hits divided by the number of bats, right? And it's a sample proportion, okay? It's a sample of all the possible at bats he could have had, right? So what he actually gets is a sample percentage. Okay, so first of all, they want us to describe, so if this batter is really a 347 hitter and he has 600 times he bats in a season, what does the distribution of possible batting averages that he could have look like? Well, again, we're looking at a sample percentage, so we know what sample percentages are. They have a normal distribution, right? And we know how to find the mean and the standard deviation, because the mean is the true population percentage, which we're given, and we find the standard deviation using that value and the sample size.
I have a question.
Yeah.
I thought the quote unquote normal distribution. Oh, wait, never mind. Because if it's normally distributed, it goes around the mean. The mean does not have to equal 0. Never mind.
Right, so so if you're looking at the standard normal has a mean of 0, but in general, means like if you look at mean IQ, okay, the IQ has a normal distribution, the mean's 100. I mean, we hope it's not 0, right? That means half the people have negative IQs. And I know sometimes there are some people that you kind of wonder about, but there is no such thing as a negative IQ. Okay, I'm going to change my sample size. Easy peasy, right? And there we go. So first of all, I know that it has a normal distribution because the central limit theorem conditions are satisfied. And if I took the time to go through those, and it's a good idea if you do it, you'll see that they are. So therefore we know it's normal, it has a normal distribution. It's bell-shaped. Well, they all say bell-shaped. It's centered on the mean. It's never centered on a standard deviation. So that rules out everything except B and D. And it has a minimum of 0 and a maximum value of 1 standard deviation. Well, that's nonsense, okay? We don't know what the minimum value is. A normal distribution goes on forever, by the way. It goes on from negative infinity to positive infinity. There is no minimum value. Technically, for batting average, it does have a minimum value. But the maximum value, 1 standard deviation above, no, of course not. So here's D. Okay. Good job. So just to say one word quickly, okay? Normal distribution is a model. The data never has a normal distribution. Well, I shouldn't say never, but very rarely do things have normal distributions. IQ does not have a normal distribution, right? Because normal distributions go on from minus infinity to positive infinity. And again, you know, people don't have negative IQs, but it's a model, okay? It approximates really, really, really well the actual distribution, okay? So it isn't reality, it's a model, but it's a very good one. Okay, so now we're playing the same game. Would a batting average be unusual, okay? And again, all I have to do is change my mean and standard deviation, and I already know what they are from above. And I'm going to compute that 3 standard deviation window. So you're going to go ahead and put in whatever the actual batting average is, and then you computed the standard deviation up here, and I'm going to enter it, although I should copy and paste the formula, but I'm just going to do it that way. I got one too many zeros. And now it's giving me this 3 standard deviation window, right? And there it is. So values within the 3 standard deviation window are not unusual. So it means this guy could be a 400 hitter, which in baseball is unheard of these days. Nobody even gets close to that. Okay, but it is possible. Wouldn't be unusual. So notice that 366 lies within my three standard deviation range interval, and so does 366. Okay, so neither one would be unusual. And in this case, it turns out that they're actually 1 standard deviation. So you notice that they ask you how many standard deviations. How could I figure out how many standard deviations these values are? So they're actually giving me values here, right? So they're giving me a data value of 0.328. How could I find out how many standard deviations away? Well, isn't that the z-score? Right? So the z-score tells me that I take my value, subtract it from the mean. Oops. I'll go ahead and click on it really quick. And then divide by the standard deviation. And notice that this is, hold on. Oh, I didn't divide by yet. Somehow that got erased. Standard deviation. And it's about 1 z-score below, which tells me it's 1 standard deviation below, right? Z-score tells me how many standard deviations I am above or below the mean. And I can do the same thing with the other value, which in this case was 366. And again, all I have to do is change this. And I see it's 1 standard deviation above. And that's definitely not unusual. Because if you go back to the empirical rule, it says that 68% of the data values are in there. So it isn't unusual at all. So they are not unusual. They're 1 standard deviation from the mean, so I can take out the ones that are 3 standard deviations. It turns out it's these 2. And therefore it's not unlikely. And then all hangs together. So any problems that we're having at this point, any issues that we're running into? Okay. All right. And this is actually showing that picture that I showed you a little while ago, right? In the PowerPoint. These are 2 different sampling distributions. What is the difference between these 2 sampling distributions? What do you think? Sample size, right? Notice what's happening. The standard deviation is getting smaller. So the 3 standard deviation window, where all of my data values should fall, is also getting smaller, which means that when I have really large samples, the estimate can't get very far away from the population parameter. And guess what? That's what I want, right? So here I'm going to do a straightforward calculation. All I'm going to do is compute the standard deviation because they've actually given me the population proportion, right? So I go to Excel and scroll over, change this to 0.5. And the first one has a sample of size 100. And so I get the standard deviation, 0.05. So see, there's nothing special about the sampling distribution. It's just another normal distribution. It just happens it's a normal distribution that describes the estimators, but there's nothing mystic about it or whatever, right? And you guys have already done calculations with normal distributions. So it isn't even anything new. And there's my new standard deviation. Okay. And we got it right. Okay. Let's see. Oh, so explain why the sample proportion would be likely to fall between, and again, you're looking at this. If I look at the first one, okay, the standard deviation is 0.05. So the 3 standard deviation window is 0.15, right? Which means that values should be between 0.35 and 0.65, right? If I take 0.5 and I multiply this by 3, 0.15 below 0.5 is 0.35, and 0.15 above 0.5 is 0.65. Okay. So again, and you can check that that's also true for the other one, but it is. The sample proportion doesn't have to be close to the population proportion. If the sample size is small, the standard deviation is really large, and it's easy for sample proportions to actually be very far away from the population proportion. And to say that the sample proportion is very likely to be equal when n is larger, that's not really giving us enough detail, right? All right, great. And explain how the results in part B indicate the sample proportion is closer to the population proportion when the sample size is larger. So notice these 2 windows, right? This is the 3 standard deviation window right here for when the sample size is 100. And notice it's very broad, right? Even though the population percentage is 50%, it's not unusual to have values between 35 and 65%. Why? Because the standard deviation is larger, so that 3 standard deviation window is larger too. Whereas when the sample size goes up to 2,000, notice that if I'm outside of this 3 standard deviation window, it's unlikely. So the majority of values are going to be between 47 and 53%. So let's see which of these. When n is large, the standard deviation is smaller. So we can rule out, in my case, B and D. Standard deviation is not larger. So the interval is smaller. And again, this is what the central limit theorem is telling us. As n becomes larger, standard deviation is smaller. 3 standard deviation window that contains all the values is smaller. So the interval is 2. If you have any questions about anything, let me know, okay? All right. I want to do 2 problems later on. I'm going to go ahead and I'm going to skip 10 because we've kind of already done 10. I want to look at 11. Okay, so here it's talking about a marketing survey conducted to see which students, whether or not students can distinguish between 2 different brands of soft drink. And the task is to correctly identify the brand tested. And a random sample of 190 students are given. They used to have the Coke Pepsi test, right? So they give 190 students the Coke Pepsi test, or they're blindfolded. They have to taste one and tell if it's Pepsi or Coke. And assuming the students have no ability to distinguish between the 2 brands, so if we pick one brand, say Pepsi, the probability the person's going to get Pepsi correctly is 50%. Okay. So first of all, I'm going to go and I'm going to, I know that the sample percentages are going to be normal, right? And I'm going to change my sample size down here to 190. And so if students can't distinguish between the 2, and I take a random sample of 190, the sample percentages are going to be centered at 50%, have a normal distribution, and they're going to have a standard deviation of 3.6% roughly. So now now it's asking me, what is the probability that I'll get a sample percentage between 50 and 55%. Now we have to use StatCrunch. So I'm going to go over to StatCrunch. And I'm going to go to normal calculator, right? Log me out. I hate when it does that. I get back in. So go to StatCrunch if you're not already. I have to log back in because it logged me out. And go to the normal calculator like we've done in module 4. And so I'm going to go to Stat Calculator Normal, just like we did in Module 4. And now I have to tell StatCrunch what my mean and my standard deviation are. But that's what you computed using your Excel sheet, right? So the mean is 0.5. And the standard deviation here was, for my case, was 0.0363. Okay? And it wants the probability that you're between two values. So remember how we do that in StatCrunch, we click between. And in my case, it wanted the probability that I'm between 50% and 55. I'm going to type 0.5 and 0.55. Okay. And now I hit compute. And so this area here is this value. Remember, areas for normal probabilities are probabilities that I'm in that interval, the area under the curve in that interval. So this roughly says about 41.6%. Okay, that's the probability. Okay, questions that we're having. Questions always come up on this one, which is why I'm doing it. Everybody's good. Is anybody awake?
I'm awake, yes, but my brain feels like nothing.
You're here.
I'm good.
Good. I just want to make sure. I want to make sure.
We're alive.
I'm sorry? Okay, you're alive. Okay, good. I'm glad. I always worry about that. Okay, so we'll go and check our answer. Okay, so check your answer. Make sure that you're getting it right. Okay, because this is a sort of calculation that is a classic problem for an exam. So I don't want to go on until everyone's done this and we're sure. Oops. Yeah, I know what the answer is. Let me make sure. Maybe I didn't enter enough decimal places. Let me see. 0.555. Let me check my calculation really quick. 0.0663. Maybe I needed more decimal points. That's maybe why it threw me off. Let me try a little more decimal points. 274. Shouldn't be that sensitive. Let me see. Yeah, it actually affected it. So word to the wise. You might want to put in your standard deviation to more than 4 decimal places. That's what got me. So I put the standard deviation into 4. So you might want to take it out to 6. Okay. So the next one's a little tricky. So it wants the middle 90%. So let's go back and look at a normal distribution and think about this, right? It wants the interval that contains the middle 90%. Well, if it contains the middle 90%, remember the normal distribution is symmetric. So 10% is in both tails, which means 5% is in one tail. So what I want is I want the values for the 5th percentile and the 95th percentile. That's the logic here, okay? So I'm going to go back to standard, And I'm going to say, I want the value such that the probability you're less than that value is 5%. Okay? And that's going to be the value right here. And I can copy and paste that right into StatCrunch. So middle 95% means that this has to be the 5th percentile and the upper value has to be the 95th percentile. So now I'm just going to change this from 0.5 to 9.5 and I get the other value. 0.55, and it's actually going to be 9.7 with the rounding off deal there. Okay, and there we are. So I want everyone to do that. I want to make sure, and we'll stop here. I'll actually work on and do the last problem, and I'll post a video. But I want to make sure that everyone gets this problem right because this is a classic sort of problem. And there we go. Actually, I'm not sure what they want for this question. I'm glad I went a little further. So we just figured out the 90% interval here. There's a 90% probability that a sample percentage will be contained within. I think they want the population percentage. No. I think they want 45. They want this the answer on the percentage on both sides. So, do they want me to answer the interval for the interval? Maybe the interval. Let me just try that. Round to 1 decimal point. I guess I'm just not sure what they're asking here. So let me just try the interval. Although I don't think that's what they wanted. Use the values. Yes, I got the values in the previous step. I'm just going to try 90. Let's just try 90 and see. I'm curious. Oh, they want the width of the percentage. That's what they want. Okay, they want the width of this percentage. So notice that the width is around 3.6 here. Okay, that's what they want. So they want you to subtract this from this and calculate the length. Okay, that's what they're looking for here. Okay, my bad. What is the probability that the sample percentage of correct identifications is greater than 65%? Remember how we do that? We change that from less than to greater than and put in 0.65. And we see that it's actually very, very, very small. Okay, so if we round this to 4 decimal places, we're probably going to get 0, right? 0.0000. And we'll check and see. Okay. Whenever you get a really small answer, you should always think about whether you entered things correctly. That's why I went back and checked. And so here, this is the same sort of thing. They're giving you 2 different values, and they want to know which is more likely. And again, you're going to compute the z-score just like we did here, okay? So you know the mean, you know the standard deviation, you can compute the z-score. The one whose z-score has the larger size is going to be the one that's less likely to occur. That's the more extreme value, okay? Okay, I think that's pretty good for today. So we can probably pretty much call this a day. And hopefully this will help as you're doing the homework, okay? Any questions or anything we want to go over before we end up?
More of a question on like the grading and stuff, but is this like a required assignment that's due with the homework, or is it a separate grade, or how does this work as far as like where the grade goes?
So notice that it's not synced to Canvas, and just for that purpose, I don't want people to be confused. This is why it says practice. This is purely extracurricular, okay?
Okay, so this is not like required to turn in. It's to like help you learn it, sort of a thing.
You don't have to turn it in, but what I will tell you is there's a very high correlation or a very high association between people who do the practice problems and the people who do well on the exam. So a word to the wise.
Okay, thank you. We'll use it like exam review.
I'm sorry?
Use it like exam review.
You can use it for exam review. It'll especially help you on the homework, but I keep it open so you can use it for the exam review too. It's an excellent point. That's right.
Okay.
Okay. I will see all you fine folks next week. And if you have any questions, feel free to ask, okay? All right. Thanks.
Thank you.